All right, so the Python is a one-liner this week, and so I'm also going to do it on Desmos. The strength of Desmos is it shows you a great graph as you're going, so it's a little bit easier to understand what the heck you're talking about. Um, but you really only need this one slide. So what we're doing is a hypothesis test for a mean. So we're picking one of our quantitative variables, finding some source in the internet about what the average of that particular quantity is. And I'm seeing here that this is sibling count. So I'm going to change that right now. Um, and then you're going to say, well, okay, well, my data, and the way you would find out what the average of your data was to do that describe method again. So I'll show you that when we get to the Python. But for my sibling count variable, it says that the average number of siblings in AdHealth was 2.88, basically. But this article is saying that the average number of siblings was only 2.44. And so I think that this is enough evidence to show that it's actually higher than that. And so that's the hypothesis test I'm going to run. And you don't have to do both of these. You pick which one kind of makes the most sense to you and the one you want to show off. They're having the same results, and so your conclusion is the same in each case. And I'm going to do both just to show you kind of how to do both. So I'm going to start with the Python. And so the deal is that, you of course have to have your assumed mean, and then you use the data to see if this mean is so high that there's basically not enough chance that you can get this sample mean if the population mean was really at 2.44. And so looking at my Python, the first thing I did is make sure that I have my quantitative variables data managed and everything. And I basically copied from last week, because remember last week we set up with all 4 variables, basically just the information to do kind of anything that we're doing with those variables. And I left the formatting of my categorical variables. I don't really know why. I don't need that. But I wanted to get this, and I looked at the kind of the sheet that gives us when we did what, and it said that in week 6 we did statistical measures. So I went back to my week 6 file. Here it is, week 6. And I saw, oh yeah, that's the describe method. So I copied and pasted that particular command, and I did it right here. And that gives me this table that shows clearly what the mean or average of the sibling count variable was. Now I could have just done mean here. I could have just put mean, and it would have just given me the mean. That's perfectly fine. But for whatever reason, I kind of like the describe better. It gives us a better sense of more stuff, and it has the mean there. So I use describe. So then you look down here, and again, you have to import something. And what it is this stats package that has this method t-test. And the reason we're doing a t-test is if your sample size is small enough, and this one isn't small at all, it's 5,100 people. So if we were able to do a regular z-test with this, it probably would have come out the same stuff. But I couldn't find a z-test on Python. And a t-test takes into account if your sample size is too small, it adjusts that normal distribution. It's not quite normal the smaller your sample size is. The bigger your sample size is, the more the distribution used by the t-test is identical to what's used by the z-test. So no harm in doing a t-test all the time for a quantitative variable. And so what the heck, that's what I'm doing. So this NaN policy to omit all the NaNs, that's kind of important. Otherwise, it's somehow including the stuff that we data managed out over here and turned into NaNs. So we don't want that. So we're going to omit all the NaNs. I'm doing a right-tailed test, right? Because I'm trying to get evidence that the mean is actually higher than 2.44. And I put that null mean or that assumed mean right there. And I put what the variable is that I'm actually doing this hypothesis test with, and it gives me the number of standard deviations above the 2.44 that my sample mean is. and it gives me the p-value, which in this case is super small. Again, it's 40 zeros. So 0.00000, altogether 40 zeros up there. So there's a lot of zeros before this 762. So that's absolutely less than zero. I'm sorry, absolutely less than 5%. So we're assuming a significance level of 5%, and all we need is a p-value less than that, and bada bing, bada boom, we have our evidence that that mean is actually greater than 2.44. So that's what I've put here. This is basically zero, so there is enough evidence to support that the mean is greater than 2.44. So that's the Python. I want to do it on Desmos as well, so I'm going to go through on my hypothesis test, not for a proportion, that's week 12, but for a mean, and I'm going to go to this calculator. Don't worry, I'll publish it before you guys get a chance to do it. And so this is set up with a particular problematicon. So I have to adjust that stuff. So my mu is my assumed mean. So that's 2.44. My sample mean, that's my 2.8. I already forget. So 2.879, blah, 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 blah. I'm going to copy that. Oops. And put it over here for the X bar. That's the sample mean. The sample standard deviation. Now's where I really do need my describe, because here's the standard deviation. So I wouldn't get that if I just did the mean right here. So if I'm going to do Desmos, I really do need the sample standard deviation. So I'm going to put that in. And then the sample size, n equals 5,000, I forget, 5,103. There we go. And what we see here is our something fishy, honestly, because why is it? So I'm going to have to redo this thing. Oh, I know why. Never mind. I'm not going to have to redo this. So that's setting up the information, but I haven't set up actually getting the p-value. So let's just go through all these folders a little bit. So it figures out, based on this formula, what the standard error would be, the standard deviation of the sampling distribution. So it calculates that, calling it S sub X bars, so the standard deviation of all the sample means. And then it just says, okay, well, our particular value for the sample mean minus the assumed mean over that standard deviation gives you how many standard deviations above the mean this is. Now, over here is where you actually are going to put in your stuff so that this can figure out what the p-value is. And what this needs to be is the t-score, because this is a standardized showing t-scores, not showing actual data. You're like, well, where's the sample mean on this problem, right? It's not there. What it's using is what would the t-scores be based on all those X bars that you would get, in particular, our sample mean. And so we need to take this value and copy it and paste it over here. And when I do that, check it out. It's way over here someplace. 13 point something. I should probably have it highlight here like I did in the other one, but probably not time for that right now. So it's over here, way over in the right tail. And the area is super small, less than zero. Not less than zero, less than 0.05. I'm sorry, it is Monday morning. And so here's that information that I've plugged in. Now this is a little bit different when I did this before. So I'm going to adjust this to reflect what I've put in here. And I don't know what I did differently back in the day. But I'm going to adjust this and have it reflect what we just came out to. Because I'm noticing that this value, 7.617, is more or less what I'm getting on Desmos as well. It's basically the same thing. So that's kind of encouraging. All right. That's it. I will talk to you guys later. Bye.